Hello and welcome to Chemistry with Dr. Clark. In this video, I would like to talk about how would you use a Bohr diagram to predict the formula of an ionic compound. So the question that this is related to, if I give you a random metal and I give you a random non-metal, can you decide what the ionic formula is going to be? Think of like sodium chloride, salt. Okay, that actually is the first example. Sodium chloride is one of those compounds that you have a lot of experience with. It's just table salt. And pretty much everybody knows that its formula is NaCl. One sodium, one chlorine. So my question is, why is it one sodium and one chlorine? And if I give you a combination that's different, let's say I gave you calcium and nitrogen, would you be able to predict how many calciums and how many nitrogens are part of that ionic formula? So to do this, we're going to use some Bohr diagrams. Now, if you're not totally comfortable with Bohr diagrams, I do have a video that talks about drawing Bohr diagrams. You should watch that first and then come back. Okay, so let's answer that question. If I have some sodium atoms and I have some chlorine atoms, I would like to predict the ionic formula that I'm going to get. So what I'm going to do is I'm going to draw the Bohr diagrams. Now, this will require a periodic table. So you will have to pull one out. If you're doing a chemistry course, undoubtedly, whoever's teaching it to you has provided you with a periodic table. So if I look up sodium, sodium is element number 11. And because it's element number 11, it would have 11 protons. If I look up chlorine, chlorine is element number 17, and therefore it would have 17 protons. Okay. Now, these are both atoms. Ignore the bottom for a moment. If you're an atom, you are electrically neutral. That means your number of protons and your number of electrons match. They have the balance. So if you've got 11 protons, then you should also have 11 electrons. Now, the video on Bohr diagrams does talk about how the first orbital, the first ring, can hold 2 electrons. So out of my 11, the first 2 live here. So you had 11, you've just dosed up 2, so you're down to 9. The second ring, or second orbital, can hold 8 electrons. I've got more than 8, so this ring is going to be completely filled with 8 electrons. 1, 2, 3, 4, 5, 6, 7, 8. First ring holds 2. Second ring holds 8. So I put in 8. I've got 1 left. This third ring, third orbital, can hold 8 electrons. But I've only got 1 left, so let's put 1 electron there. Okay, let's move over to chlorine. The chlorine has 17 protons. Therefore, it would also have 17 electrons. To be electrically neutral, the number of negatives and positives have to match. So, first ring, I can put 2 electrons in it. I had 17, I just used up 2, so I'm down to 15. The second ring can hold 8. I've got way more than 8, so let's put 8 here. 1, 2, 3, 4, 5, 6, 7, 8. Okay, so I used up 8 more, I'm down to 7. This outermost ring can hold 7 electrons. Can hold 8. But I've only got 7. So there's enough room in this third orbital to hold all 7. So let's put them in. 1, 2, 3, 4, 5, 6, 7. So what I've got now is a Bohr diagram for my sodium atom and a Bohr diagram for my chlorine atom. Neither one of these are particularly stable. Okay, there is a video on how you form ions based on their number of valence electrons. So what I'm going to do next is based on that video. So when I do this next step, if you find that it's still a little confusing, you should go back and look at the video that talks about predicting ions and ionic charges based on valence electrons. Because the idea here is that an atom is only really stable when all of the rings or all of the orbitals are filled. So if every single ring was filled, you would be energetically stable. You'd be low energy, you'd be happy. You can see that here in the sodium, the outermost ring is not filled. You can see for the chlorine, the outermost orbital is also not filled. These would be your valence electrons, right? Sodium has 1 valence electron, chlorine has 7. Now, this is a match made in heaven, because the easiest way for sodium to end up with all filled orbitals is to give this electron away. Because if it gives this electron away, you've got the first orbital filled, you've got the second orbital filled, and the third orbital has nothing in it, so you don't need to draw it. Right? If I can give that one electron away, everything appears to be filled. Well, what is the chlorine missing? The chlorine's missing 1 electron. If it could gain 1 electron, its outermost ring would also be filled. Right? That's why I say this is a match made in heaven. Sodium really wants to give 1 electron away, and the chlorine really needs 1. So when they come close to each other, that's what they do. The electron will jump from the sodium to the chlorine. Now, let's draw an after picture. This was before. Let's do after. You've still got 11 protons. You've still got 2 electrons in the first ring. You still got 8 electrons in the second ring. 4, 5, 6, 7, 8. And because you gave away this electron, you don't need the third ring. So this sodium now has all filled rings, all filled orbitals. It is energetically stable. It's happy. It does give it a charge, right? If you've got 11 positive protons, you only now got 10 negative electrons, right? 2 plus 8. So if you've got positive 11 and a negative 10 and you put them together, that gives you a positive 1. So your sodium ion would be a sodium 1 plus. Let's do the after picture for the chlorine. In the after picture, you've still got 17 protons. You still have 2 electrons in the first orbital. You still have 8 electrons in the second orbital. And your outermost orbital, your valence electrons, you used to have 7, but now you've gained 1 extra one. So now you have 8. 3, 4, 5, 6, 7, 8. Because you gained that extra 1, every single one now of these orbitals are completely filled. You're happy. You are energetically stable. So let's count up what your charge is. You had 17 protons. You now have 2 plus 8 plus 8. You have 18 negative electrons. That's like saying positive 17. This is like your negative 18, right? If you got a positive 17 and you add it to a negative 18, you get a negative 1. So your chloride ion is a minus 1. And it kind of makes sense, right? If your sodium lost an electron, it became a plus 1. The chlorine gained the electron, so it became a minus 1. And the combination that makes everybody happy, you only need 1 sodium and 1 chlorine to transfer 1 electron, and everybody becomes happy. That's why, if you put sodiums and chlorides together, you only need 1 sodium and 1 chlorine. Because this whole process only involves 1 sodium and 1 chlorine. Now, the reason why they do hang around together after they've made the transfer, this is positively charged. This is negatively charged. If you've got a positive and a negative that are close to each other, and they had to get close in order to transfer that electron, positives and negatives attract, so the minute they transfer the electron and they become positive and negative, they attract each other and they're trapped together. That's how you make your sodium chloride. All right, let's try a second example. Let's say that we would like to put together some calcium atoms and some sulfur atoms. Okay, that's the 2 things that I'd like to put together. So again, if we pull out our periodic table, calcium is element 20. So it would have 20 protons. Sulfur is element 16. So it would have 16 protons. Now in the world of atoms, you are electrically neutral. So if you've got 20 protons, that means you have 20 electrons. 2 go in the first ring. So that's 2, leaves you at 18. 8 go in the next ring. 1, 2, 3, 4, 5, 6, 7, 8. That's another 8 electrons, so I'm down to 10. The third ring can hold 8 electrons, so let's put 8 electrons there. 1, 2, 3, 4, 5, 6, 7, 8. Now, you still got 2 electrons left over, and I've run out of rings. So maybe let's just sketch in one more ring. My circle drawing ability is not the best, so I'm going to draw a partial ring, but you can imagine that it goes all the way around. And then my last 2 electrons will live out here. Now, if I look at this, the inner ring is completely filled. That's good. The second ring is completely filled. That's good. The third ring is completely filled. That's great. But this outer ring is not completely filled. It only has 2 electrons. Now, to be completely filled, you can either add electrons or you can remove them. If you have 1, 2, or 3 valence electrons, it is much easier just to lose them. Okay, if you have 1, 2, or 3, you like to lose. So these 2 electrons here, I know that I'm going to try and get rid of them. So let's move over to the sulfur. Sulfur has 16 protons, so it would have 16 electrons. 2 go in the first ring, so subtract off 2 leaves me with 14. 8 go in the second ring. 5, 6, 7, 8. So I've used up 8 more, and I'm down now to 6. Now this third ring can hold 8 electrons, but I've only got 6 left. So let's put 6 there. 1, 2, 3, 4, 5, 6. Neither one of these are energetically stable, right? This has an unfilled outer ring of electrons. It's got 2 valence electrons. This has an unstable outer ring. That outer ring only has 6 electrons. It would really like to have 8. So, again, it's another match made in heaven. These two are perfect for each other. This calcium wants to give away an electron, and the sulfur would really like to have it. The calcium would like to give away a second electron, and the sulfur would really like to have a second one. Right? You've got 2 to give away, and you're missing 2. Perfect match. So, if we redraw our picture with the changes, this was 20 protons. You still got 2 in the first ring. You still have 8 in the second ring. And I do need a third ring. There we go. My third ring also still has 8 electrons. There we go. And the only ones that I've lost are out here in this fourth ring. They're gone. And so now I have 3 rings that are completely filled. This is energetically stable. It's happy. The charges don't balance though. I had 20 protons. I used to have 20 electrons, but I gave 2 away. That means I've only got 18 electrons left. So if you've got a plus 20 and a minus 18, that's going to give you a positive 2. So my calcium ion is a calcium 2+, because you lost 2 electrons. If we redraw the sulfur as the sulfide, that's a 16 positive protons. You still have 2 in the first ring. You still have 8 in the second ring, or orbital. And your last orbital, you used to have 6 valence electrons, 6 outermost electrons, but you're going to add 2. So 6 plus 2 will give me 8 valence electrons. 8 electrons in this outermost ring. Every single one of the rings now are filled, energetically stable. If we count up the charge, you had 16 protons, and now you've got 2 plus 8 plus 8. You've got 18 electrons. That's like saying 16 positives, 18 negatives gives you a negative 2. So my sulfide would be an S minus 2. Again, it still makes sense. You lost 2, so you became 2 positive. You gained 2, so you became 2 negative. And this is a match made in heaven. Your calcium is now happy. Your sulfur is now happy. And this happiness only involved 1 calcium and 1 sulfur. So your ionic formula would be CaS, 1 calcium, 1 sulfur. Now I should point out that the calcium is a 2+, right? It has a 2+ charge. Your sulfur is a 2-, it has a -2 charge. This calcium still has a +2 charge. This sulfur still has a -2 charge. But if you put two things together that has a +2 and a -2, they cancel each other out. That's why we don't write the charges here. Because even though it is a +2 and a -2, +2, -2 cancel. So we don't bother to write it down. So even though it's not written, still +2, still -2. And like before, to get close enough for these to transfer electrons, puts a positive thing and a negative thing really close, and positives and negatives attract. So these two ions now will stay together. So your ionic formula would be calcium sulfide. This whole process just requires 1 calcium and 1 sulfur. Okay, let's stop doing the easier ones and let's do something a little bit harder. Let's say that we want to talk about lithium atoms joining with oxygen atoms. So if we haul out our periodic table, lithium is element number 3, so it has 3 protons. Oxygen is element 8, so it has 8 protons. If you have 3 protons, that means you have 3 electrons. 2 in the first ring and 1 left over. Let's put the leftover one here. So you have 1 valence electron. Valence electrons are the outermost electrons. If you have 8 protons, you have 8 electrons. So 2 in the first, 1, 2. That leaves you with 6. This next ring can hold 8, but you've only got 6. So 1, 2, 3, 4, 5, 6. Now, I did draw a third ring, which I don't need. I got a little carried away there. Maybe I should have saved it and used it for the last example where I was missing a ring. So for this thing here, you do have 1, 2, 3, 4, 5, 6, 7, 8. For this thing here, you have 6 valence electrons. You would really like to have 8. Now, if we do the trick that we did in the last one, right? Lithium's got this extra electron. It would really like to give it away because if it gives it away, it'll appear to have only filled orbitals. So it's going to give it to my oxygen. Oxygen's like, hey, I had 6. If you give me 1 more, I'll have 7. I'm closer to having 8, but it's not a perfect match, right? Lithium gives away 1. Oxygen gains 1, but oxygen still needs another one, right? In order to have 8, this oxygen needs to pick up 2. It has 6 valence electrons, and so it needs to pick up 2, which means that 1 lithium is not going to do it. What I really need is 2 lithiums. So if I draw myself a second lithium, 3 protons, 2 electrons in the first ring, 1 electron in the outer ring. In order for this lithium to become energetically stable, it would like to take this electron and give it away. If it gives away an electron to the oxygen, it becomes happy, stable, right? Because this outermost ring that has 1 electron, it loses the electron and therefore it just disappears. So you only have 1 ring with 2 electrons, which is filled. By having 2 lithiums, I get 1 electron from the first lithium, I get 1 electron from the second lithium, and therefore my oxygen picks up the 2 electrons it needs, right? Gets 1 electron from the first one, it gets 1 electron from the second. So now it'll have 1, 2, 3, 4, 5, 6 valence, plus it's going to get 2 extra ones. In order to make this work, I need 2 lithiums to go with my 1 oxygen, because each lithium only gives 1 electron, but the oxygen needs 2. So if we summarize our results, the lithium gives away this electron, so it's left with only its 2. That is a completely filled ring, filled orbital, so it's happy. It is a 3 proton, but only 2 electron thing. So that gives you +3, -2, gives me a +1. So this lithium has a +1 charge. This lithium over here, 3 protons. It has 2 electrons in the inner ring, which it keeps, but it gave away the other one. So for this one, your outer ring, your only ring, is completely filled. And again, you have 3 protons, but you only have 2 electrons. So positive 3, negative 2 gives me a plus 1. So the charge here is also going to be lithium plus 1. Now, if we redraw our oxygen, you've got your 8 protons in the center. That first ring had 2, it still has 2. The second ring had 6, but you've gained 2 extra electrons. So this second ring now has 8. 8. And again, I apologize for having the extra ring there. I got carried away and thought I'd need it, but I didn't. So if you ignore that outer ring, first ring has 2 and it's completely filled. Second ring is filled, it has 8. So your oxygen is good. Your oxygen is now all completely filled rings, and so it's energetically stable. If we talk charges, this thing had 8 protons. It now has 2 plus 8 is 10 electrons. So that's like saying you've got a positive 8 and a negative 10. If you had a negative 8 and positive 8 and a negative 10, you get a negative 2. So your oxygen ion is an O2 minus, which again makes sense. In order for this lithium to have a plus 1 and this lithium to have a plus 1, then your oxygen has to balance it out with a minus 2. The total amount of positive charge has got to equal the total amount of negative charge. In the last example, if I can find my last example, here we go. See, I had 2 positives and I had 2 negatives. The 2 charges balanced. If I look back to the original first example, I had a positive 1 and a negative 1. So for this one here, the total positive and the total negative balances, but it's spread out over 2 lithiums, right? I've got positive here and positive here. That gives me 2 positive to go with the 2 negative. In order for this whole thing to work out, in order for both lithiums to lose the appropriate number of electrons, in order for the oxygen to gain the appropriate number of electrons, I needed to have 2 lithiums and 1 oxygen. So if you have lithiums and oxygen together, it's going to be 2 lithiums and only 1 oxygen, Li2O. When you write the formula, it is always the metal first and the non-metal second. So metal is the lithium, non-metal is the oxygen. All right, let's try one more. And just based on this, you can see that it gets kind of complicated. If we're going to talk magnesiums and we're going to talk about nitrogens. Magnesium is element 12. So it has 12 protons. If you look at nitrogen, nitrogen is element 7. It has 7 protons. Now, in the last couple of examples, I put the before picture on the top and the after picture on the bottom. For this one here, because space is kind of short, because I have so much stuff to do, I've decided to go with left versus right. The left side are the atoms. The right side is going to be the after picture with the ions. Okay, so if you have 12 protons, that means you have 12 electrons. First 2 go in the first ring. The next 8 go in the second ring. That gives me 10. 2 plus 8 is 10. That means I've got 2 left over. 1, 2. Because you have 2 electrons, you're going to want to give those away, right? If you have 1, 2, or 3 valence electrons, electrons in the outermost orbital, then you are going to want to give those away. If we talk about the nitrogen, nitrogen has 7 protons, which means it has 7 electrons. So let's put in my first 2. If you've put in 2 and you had 7, that means you got 5 left. This outer ring can hold 8, but you've only got 5. So 1, 2, 3, 4, 5. Now, I have strategically placed them all on this side of the atom because I know that I'm going to transfer, and so I want to keep the space on this side of my atom so that way I can show the transfers. Now, you can see here why I've had to draw so many. This is a terrible match. The magnesium wants to give away 2, so we'd like to give away 2. But your nitrogen already has 5. It's looking for 3 more. So it's looking for 1, 2, 3. right? That doesn't match at all. I can transfer my first electron, I can transfer my second electron, but I don't have a third one. So the magnesium can become happy, it can become energetically stable by losing its 2 electrons. But currently, the nitrogen is not happy. It had 5, it's going to end up with 6 and 7, but it's still missing 1. So if you're still missing an electron, that means I need something else to give electrons away. So if the first magnesium gave some electrons away, I'm going to need a second magnesium to give away electrons. So let's just copy our magnesium. 12 protons, 2 in the first ring, 8 in the second ring, and 2 valence electrons. Okay, this magnesium would also like to give away those 2 electrons. The first one moves very nicely here. Right, this nitrogen needed 3. It got 1, 2 from the first magnesium, and it's going to get the third one from the second magnesium. So, this magnesium, perfect. This nitrogen, perfect. This magnesium, not happy. It wanted to give away 2, it gave away 1, but it still needs to give another one away, and it's got like nobody to give it to. So if you've got an electron to give away, you're going to need another atom that's willing to accept them. If the first nitrogen accepts electrons, then you're going to need a second nitrogen. So let's draw another nitrogen. 7 protons, 2 electrons in the first ring, 5 electrons in the second ring. 2 plus 5 is 7, so you got 5 valence electrons. Just like this one, if you've got 5 valence electrons, you're looking for 3 more. 5 plus 3 will give you 8, which is a full orbital. So now I've got a place for this electron to go, right? This extra electron will go here. It gives 1 electron to the first nitrogen. It gives 1 electron to the second. So now this magnesium, energetically stable, it's happy. The new nitrogen you drew, not so happy, right? It picked up 1 electron, but it's still missing 2. So if you still need more electrons, that means you need more atoms that give electrons away. If the first magnesium gave away electrons and the second magnesium gave away electrons, then you're going to need a third magnesium to give away electrons. So let's draw a third one. 12 protons, 2 electrons in the first ring, 8 electrons in the second ring, and 2 valence electrons in the third ring. These 2 electrons would like to be given away. And finally, things match up. You are looking for 2 and you have 2. So this electron goes here and this electron goes here. This is one of the hardest ones to do. Whenever you have like, I have 2 electrons and I'm missing 3, or if I had 3 and I'm missing 2. The 2 versus 3 thing is probably the most difficult problem. Now, let's summarize what we've done. So if I redraw my magnesiums, they all have 12 protons. They all have 2 electrons in the first ring. And they all have 8 electrons in the second ring. So 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. 1, 2, 3, 4, 5, 6, 7, 8. They all had a third ring with 2 valence electrons, but we've given those 2 electrons away. So I don't need the third ring because the third ring is empty. Now if we talk charge, each of these started with 12 protons. They now have 2 plus 8 is 10 electrons. So 12 positives and 10 negatives make a 2 plus. So this would be magnesium 2 plus, this would be a magnesium 2 plus, and this would be a magnesium 2 plus. If we talk about the nitrogens, both nitrogens started with 7 protons. Both nitrogens had 2 electrons in the innermost ring. Both electrons started with 5 valence electrons, but added 3 extras. So both of them now have 8 electrons in the outermost ring. 8, 1, 2, 3, 4, 5, 6, 7, 8. So now both nitrogens are also completely with filled rings. They are energetically stable, they're happy. If we talk about the charge on these, they started with 7 positives. You now have 2 plus 8 is 10 negatives. So plus 7, negative 10 gives me minus 3. So the charge on your nitride is a 3 minus. The charge on your nitride is a 3 minus. Now I'm feeling happy because the total amount of positive charges should match the total amount of negative charges. I've got 2 plus and 2 plus and 2 plus. I got a total of 6 positives. If I look at my negatives, I've got a 3 minus and a 3 minus. I got a total of minus 6. Total positives and total negatives match. Now, looking at this, it did take a lot of magnesiums and a lot of nitrogens, but every single one of them now has completely filled orbitals, completely filled rings. In order to make this whole thing happen, I needed to have 3 magnesiums and 2 nitrogens. So the formula for this would be Mg3, because there's 3 of them, N2, because there are 2 nitrogens. So if you're looking for the formula of magnesium and nitrogen coming together as an ionic compound, you're going to have an Mg3, N2. Once again, thank you for joining me in this video, and we'll see you next time.